In this module, we will discuss some modeling challenges and how to address them. So far, we've learned how to model certain types of systems, mechanical systems, electrical circuits, from first principles. A challenge that sometimes arises is that we may not be able to derive the model for a physical system from first principles. And so one approach to address this is to use what we will call a black box modeling approach. And one example that we'll discuss in particular is using such an approach for modeling batteries. Another challenge that can arise is that sometimes the mathematical models that we've derived, the differential equation or the transfer function, cannot be solved by hand or cannot be solved analytically. And so an approach that we will learn to address those situations is numerical simulation. Black box modeling is an alternative to deriving models for physical systems from first principles. So instead of using our knowledge of physics, using Newton's second law, using Kirchhoff's laws, the idea is that we don't understand the physics of the system, or we don't attempt to understand the physics of the system, and rather we feed the system a known input and observe the output and try and fit a mathematical model that will match that output for the given input. This is something that we've discussed a little bit in the past, but try and think about or try and recall what some advantages or disadvantages of a black box modeling approach are as compared to a first principles modeling approach. One example where black box modeling is often used is with batteries. So one approach for deriving the model of a battery is to examine the sort of the underlying chemistry of the battery. This process can be quite challenging, especially for engineers who may not have the chemistry background. And as engineers, for our purposes or for the purposes of control, we don't necessarily need a physics chemistry-based model. We don't necessarily need to understand what's happening within the battery. We just want to capture the input-output behavior. We just want to know how the current being supplied by the battery will change under different conditions. Commonly, a way that this is accomplished is to model the battery with an equivalent circuit model. That is to say, we find circuit models that have similar input-output behavior to the battery. The simplest approach is to use a simple resistive model, and so that's what's shown here. And in this case, the battery is simply modeled as having some open circuit voltage, that's the voltage of the battery, and some internal resistance. This is what we would call a static model. So the model itself derives from Ohm's law. It is an algebraic model, and if the load changes, i.e. the conditions change or the input to the system changes, the output changes instantaneously, as you can see from this relationship. So if the load on the battery changes, then the current will change instantaneously. In reality, this is not a perfect model. A battery is not a static system. If the load changes, it will take time for the output to change, or the current supplied by the battery to change. It won't happen instantaneously. This simple model, however, is nice. It's very easy to use. It's very easy to solve. It can be appropriate under certain conditions. The amount of fidelity that it provides could be sufficient if you are just looking for approximate results, or if the load is changing slowly. If the load is changing slowly, then treating the model as being static is appropriate. Another situation where it may be appropriate is if you're doing sort of a system level simulation. And so in this case, if you're trying to model the battery, but it's also interacting with an electric motor and the drive line, etc. What a situation you can have is that the dynamics of the battery are so fast that they get lost when you compare them to the dynamics of the other parts of the system. And this is something that may not be completely intuitive, but it's something that we will come back to later in this semester, and we will demonstrate it mathematically to try and give you some intuition for why that's the case. Here are two examples of more refined battery models. So these models capture the dynamics of the battery. If you change the load, the current or the power supplied by the battery wouldn't change instantaneously. It would take time to react. And these models are not algebraic models. They must be modeled by differential equations, and that's because of the presence of the capacitors. And so the thing to keep in mind is that these circuits aren't physics-based models of the battery. The battery doesn't literally have capacitors and resistors within it. It's just that the dynamics of these circuits, if you compared, the response of the output for a given input, would approximate the dynamics of the battery. In general, you can come up with different types of circuit equivalent models that may be appropriate for different types of batteries, a nickel-cadmium battery, a lithium-ion battery, and different models may be appropriate depending on the fidelity requirements or the accuracy requirements you may have. Most of the models that we've talked about so far, when we talked about mechanical systems and electrical systems, and then here as we're talking about batteries, we've assumed that they're time invariant. We assume that the different parameters of the system don't change with time. So for example, in the previous slide, oftentimes we would make the assumption that the open circuit voltage of the battery is constant, or the resistances and the capacitances that we're employing aren't changing with time. In reality, that's not the case for batteries or for many other systems as well. For example, it's been shown experimentally that the voltage of the battery, the open circuit voltage of the battery, is a function of state of charge and temperature. So SOC means state of charge, and it represents how charged the battery is. Has it been completely depleted, or is it fully charged? Furthermore, the internal resistance of a battery has been shown to be a function of the open circuit voltage, the temperature, and whether or not the battery is being charged or if it's being discharged. If we have a situation where these parameters are changing slowly as compared to the dynamics of the other parts of the system, then it's reasonable to treat them as constants. And again, this is something that may not be that intuitive, but we will show it mathematically later on. Here are two graphs showing how some of the parameters of a battery may change over time. And so the graph on the left shows how open circuit voltage changes with state of charge. So you can see that it varies quite a bit, from 3.1 volts to almost 4 volts. And you can also see how there's some variation with temperature. So there's 3 different traces here for 3 different temperatures, 0 degrees Celsius, 25 degrees, and 40 degrees. The graph on the right shows how the internal resistance of a battery may change with open circuit voltage and again with temperature. As was stated on the previous slide, if the parameters are changing slowly, it may be appropriate to treat them as constants or to treat them as time invariant. And so one approach that you may have is you may have a set of battery models that could be switched between based on different environmental conditions. So perhaps you use a battery, one battery model when the temperature is very cold, and a different battery model when the temperature is very warm. Other conditions under which you may be able to treat the parameters as time invariant is, again, if they change slowly compared to the overall dynamics of the system, or if the operating conditions of the system are very narrow. So for example, in practice, in an electric vehicle, we do not let the battery run all the way down to zero state of charge. We don't deplete the battery completely, and we don't charge it completely either. We keep it in a narrower band in order to extend the life of the battery. So under those conditions, if we're keeping the battery in a very narrow or a more narrow range of the state of charge, it may be appropriate to sort of treat the open circuit voltage as a constant. Here is a picture of the actual battery in the first generation electric hybrid Ford Escape. This vehicle we actually have on the McNichols campus if you ever want to see it in person. Just to give you a sense of the size of the battery, this unit basically takes up the ground of the rear cargo area of the Escape, or the area underneath the hatchback. So it's quite large. Another example is the first generation Ford Fusion, where in that vehicle the battery basically takes up the space behind the rear seat. So it basically spans the width of the vehicle. Looking at the battery, it consists of a number of cells that are arranged in series and parallel. So for example, you could imagine that this little block is a single cell, and it's connected to other cells situated around it, either in series or in parallel. Putting the cells in series affects the overall voltage of the battery. So for example, if we consider that we have a 5-volt cell and we put it in series with another 5-volt cell, it'll alter the voltage output at the terminals of the overall battery package. Recall that voltage is a potential difference. So if we start at ground, the first cell will bump us up 5 volts, and then the second cell will bump us up an additional 5 volts. So the total difference across both cells is 10 volts. Changing the voltage output of the pack can be important in determining how much voltage is needed to drive a particular motor or a particular accessory, etc. The number of cells in parallel affects how much current can be sourced. So again, if we have these two 5-volt cells, if instead of being in series they're in parallel, if you look at the voltage across both cells, the voltage across each is 5 volts, where basically this whole upper bar is at the same voltage and this whole lower bar is at the same voltage, presuming that the wires connecting the batteries have minimal resistance. So putting them in parallel doesn't affect the voltage at the output, but it does affect how much current can be sourced, because in essence, this cell is sourcing some current and this cell is sourcing some current, and the current flows sum together. And so what that affects in essence is how long the battery will last before it's depleted, and that's measured in amp hours. So if the battery is a 10 amp hour battery, that means that it can supply 1 amp for 10 hours, or it can supply 10 amps for 1 hour, depending on how you look at it. Another challenge that arrives in modeling is when you have a model that is prohibitively difficult to solve by hand or to solve analytically. Most of the models that we've seen so far are linear models, which can be solved in a closed form manner. However, most real systems have nonlinear aspects to them that make their differential equations very difficult, if not impossible, to solve analytically. And so a solution to how to address these models or how to solve these models is to approximate their solution numerically. And this is what we will call simulation. This can also be useful even if we have a linear model, but the model is too complicated. For example, an entire vehicle model with models of many subsystems working together. Such a model may be too complicated to solve by hand, but again, it's something where we can approximate the solution numerically using simulation. So far in the course, we've already seen several examples of nonlinearities. One such example was wind drag, which tends to be proportional to velocity squared, so that's a nonlinear function. Springs tend to be nonlinear, especially if you extend them beyond a sort of a narrow range of deformation. Coulomb friction, or the modeling of stiction, is another example. Another typical type of nonlinearity is something called saturation. So if we consider the horizontal axis to represent the input and the vertical axis to represent the output, you can imagine that most any physical system cannot generate sort of an infinite output. Any sort of actuator, any sort of amplifier will eventually saturate. If you have a motor and you supply it some voltage, eventually the torque or the speed of the motor will reach some limit. Another example type of nonlinearity is called a dead zone, and an example of this in a motor derives from stiction or from the Coulomb friction type of model of friction. So here you can imagine that we're supplying some voltage to the motor, but the motor doesn't move initially. And that's basically because the motor needs to generate a sufficient amount of torque to overcome this stiction friction before it will break free and start to move. And then a final type of example that we show here is something called backlash. It's also representative of a system that has hysteresis. So an example of this would be two gears that are meshing. So you can imagine that the two gears have some play, and so the input gear may move a little bit before it engages the output gear and starts to drive the output gear. And so that's something that perhaps you can sort of see here. So initially the input gear moves some before it causes the output gear to move. However, if you drove the input gear in the opposite direction, then it would have to again move a certain distance before it engaged the output gear again. And so that's what you sort of see here. It's the idea that the system behaves differently moving in one direction than it does in a different direction. As we said previously, when we have these nonlinearities present, it's difficult, if not impossible, to solve the differential equations analytically. So what we do is we try to approximate the solution. And so one very simple illustrative method is something called Euler's method. So here we have a derivative. Recall that differential equations are simply equations that have derivatives in them. And so one idea is to approximate the derivative as a finite difference. Graphically, what a derivative represents is a rate of change or a slope. So it's the difference in the change in x between two discrete instances in time divided by the change in time. If we rearrange this, we can basically try and estimate the value of x some step t, delta t, into the future. So if I solve this equation for x of t plus delta t, I just multiply the delta t to the left-hand side. I get x dot of t times delta t, and then I add x of t to the other side, and I get this approximation. And we can use this to solve differential equations. So let's say, for example, that this blue line is x of t. So this is the true solution of our differential equation. We can't arrive at this analytically for some reason. There's nonlinearities in our equation, or the equation's too complicated. And so what we do is we start from some initial condition, let's say x sub 0, and we use this approximation to try and estimate the value of x some step into the future. So at time t0, we know what x of t is. We know what the derivative is from our differential equation. Our differential equation, let's say, is x dot of t equal to something. And we're choosing some time step into the future. So if we apply this equation, we can estimate what the value of x is sometime into the future to give us an estimate of the value of x at time t sub 1. This equation is basically a linear equation, and so we're sort of extrapolating, doing a linear extrapolation out into the future. From that estimate of x sub 1, we can then perform the same sort of estimate. We have our estimate, we have our value of our derivative, we extrapolate some distance, some time delta t out into the future to get an estimate of x sub 2. And we continue to do that, and we get some approximation of the graph x of t. Logically, you can see that the true value of x of t, which is this solid blue line, is different than the approximation. But the hope is that our approximation can be sufficiently close to be useful. So looking at this, take a second and think about how we might be able to improve the accuracy of our numerical simulation, of our numerical approximation. So one way to improve the accuracy is to use a smaller time step. So to make the delta t smaller, the time between t0 and t1 smaller. Another way to make the solution more accurate is to use a higher order solver. So this Euler's method that we just used is what we call a first order solver. We're basically doing a linear extrapolation based on a single point in time. Higher order solvers exist, second order, third order, where we're not just using line segments, you're using maybe parabolas or cubics, using multiple instances of time to get a smoother, more accurate solution. So again, take a second and think about whether or not there would be any drawbacks to using these approaches to improve our accuracy. In general, the trade-off between using these approaches to get improved accuracy is that it'll take the simulation longer to run. This is a common trade-off. The thing that we always want to keep in the back of our mind is that if it takes our simulation 1 hour to simulate 1 second of time, then it's not very useful. You wouldn't be able to run very many simulations, get very much data. So one way to improve accuracy is to reduce the time step and use a higher order solver, which happens at the expense of making the simulation take longer to run. Other ways to improve accuracy is to improve the complexity of the models. And so this was something that we saw when we were talking about the battery models, whether or not to use a simple resistive model, which is very easy to solve and would make the simulation run very fast, or whether or not we should use a dynamic model, a differential equation model of the battery. In general, Some dynamics may be neglected, treated as static under certain conditions, such as if the system is changing slowly, or if the dynamics of that particular subsystem are very fast compared to the dynamics of the rest of the system. You can also use lookup tables instead of differential equation models. And these lookup tables or these maps could be based on steady state performance. So this is something that we discussed when we were looking at the torque speed curve of an electric motor. Or we could use cycle averaged efficiencies, for example, for an IC engine. Instead of modeling the entire combustion process, you just look at the average efficiency over a particular cycle. Most simulations will use some combination of these physics-based differential equation models and these empirically derived maps. And the sort of, the trade-off is accuracy with speed with which the simulation can run. In general, the form of the model that you use will be determined by the purpose of your simulation and the requirements of the simulation. How accurate does the simulation need to be? What is it that what questions are you trying to answer from the simulation? At this point, we will also discuss ways to structure your simulation, in particular for larger systems. And so one way to structure your simulation is what we will call a backward-looking simulation. And the way that this type of simulation is structured is you start with the desired tractive effort, for example, from the drive schedule. So you have some urban drive schedule from the EPA, and you basically just presume that velocity profile is being met by the vehicle perfectly. And then based on that, you work backwards and you determine what is needed from the power plant, the IC engine, the electric motor, to achieve that velocity. These types of simulations tend to run faster. They tend to make use of these empirical maps and lookup tables. The alternative is to use a forward-looking simulation. And so in this case, you start with a drive schedule, but you don't presume that it's met. You basically have a driver model that generates actual inputs to the power plant. So based on the drive schedule, you have a model of the driver that generates some braking input, some throttle input. Those are then applied to the power plant or the model of the braking system, which generates some torque. And then that torque is then applied to a model of the transmission. And then the output of the transmission generates some torque, which is then applied to a model of the wheels, and so forth. This type of simulation basically mimics the physical world. It's very useful for controls development, and it's very useful for hardware in the loop testing, which is what HIL stands for. So what I've stated so far describing these two simulation architectures may not be very clear, but on the next two slides I'll try and give some examples. Some examples of commonly used simulations for electric vehicles and hybrid electric vehicles are the package which used to be called PSEP, which is now Autonomy, which was generated by the Argonne National Labs, which uses a forward-looking structure to the simulation. There's also the Advisor simulation, which is generated by another national lab, NREL, the National Renewable Energies Laboratory, and it has aspects of backward-looking and forward-looking simulation, so we'll term it a hybrid sort of architecture. Here's an example of a backward-looking simulation. This may look familiar to you if you've taken the batteries course, but the way that it works is it starts with an input from the drive schedule. So basically this is generating velocity outputs as a function of time. And then this velocity is supplied to this block, and it's differentiated to get an acceleration. It's presumed that the vehicle is meeting these exact velocity and accelerations as provided by the drive schedule. So what's the power generated at the wheels in order to supply this level of acceleration and velocity? So this is a static model. It basically tacks on sort of the different road loads due to grade, due to air drag, and determines how much power is needed to make the vehicle meet the drive schedule exactly. This power is then used to determine how much power needs to be drawn from the battery, and it basically this block consists of just a map based on the efficiencies of the battery just tacked on, and then based on the power that's being drawn from the battery, it determines how much current that corresponds to, and then it is used to estimate the state of charge of the battery, in essence by integrating the current. And then it also is used to estimate the temperature of the battery and the values of various sort of parameters, the resistance, the state of charge, etc. This is a backward-looking model. It uses a lot of sort of static elements or empirical maps, but it does also use some physics-based models. For example, the way that the temperature of the battery is estimated is using a differential equation model from first principles. This type of simulation, or this simulation in particular, runs very fast, and it can be used to answer a lot of questions in terms of, in essence, maybe you're trying to size the battery, or maybe you're trying to determine sort of the efficiency of the vehicle. This would probably do well in those sorts of tasks. Here's an example of a forward-looking architecture. And so in this case, there is the drive schedule. The drive schedule is built in to this model of what we're saying is the preceding vehicle and this model of the driver. And so we're not presuming that the vehicle can actually meet the velocity and accelerations prescribed by the drive schedule. But what we're doing is we're modeling the driver, and the driver is taking these sort of desired velocities as inputs. It's also taking the distance of the current vehicle to the vehicle preceding it on the highway. And based on those inputs, it's generating commands. So in this case, a throttle command where we're presuming that the brake command is 0. So this is just basically only modeling an acceleration. So it takes this throttle command, and then it goes to a model of the throttle, which then goes to a model of the engine. So the throttle generates a throttle angle, which is an input to the engine. The engine generates a torque, and that goes to a model of the torque converter, which then generates a torque, which goes to a model of the wheels, and so on. And so the structure of this sort of mimics the structure of an actual physical vehicle, the flow of inputs and outputs. Each box may be modeled by a differential equation, a physics-based differential equation, but it may also use an empirical map. So for example, this engine is based on a map of empirical data. But this model is nice for a few things. So one thing is it's very helpful in doing hardware in the loop testing. Since it mimics the actual physical world, it's easy to sort of replace individual blocks by actual physical components. So you could imagine that this mathematical model of the engine is replaced by an actual physical engine. So this signal for throttle angle could be a voltage, being sent to a motor on the throttle of a test bench. So this signal could generate a signal to an actual physical piece of hardware. It can cause the engine, to move, and then you could have a sensor measuring the speed of the engine or the torque being generated by the engine, and those sensor readings could then be supplied to another mathematical model. So this sort of forward-looking architecture is very nice for hardware-in-the-loop testing. It's also nice for controller development. So you can imagine if we had a controller on this engine, or we were trying to design the engine controller, we would want it to sort of mimic the physical world. We would want it to take as inputs the same sort of inputs that it would take in the real world and generate the same sorts of outputs. And it also allows us to assess sort of the dynamic performance of the system. So if we're trying to assess, what's the 0 to 60 time, or what is the comfort level of the driver, then we need this sort of more physics-based dynamic sort of modeling. The software package we will use in this class for performing our numerical simulation is something called Simulink. Simulink is an add-on to the program MATLAB, which we've already introduced in this class. Simulink represents models as block diagrams, and an underlying solver, like Euler's method, which we introduced, is used to approximate the values of the variables. Within Simulink, you can choose the solution method, for example, a higher order solver than Euler's method, and you can also specify the time step that the simulation uses. Simulink includes a large library of different mathematical functions, including many types of nonlinearities. At this point, we will introduce briefly how to model different types of mathematical models within Simulink. It is likely you've had some introduction to Simulink in previous classes, but if you haven't, that's okay. I won't assume any prior knowledge, and if you have additional questions, please feel free to ask me outside of class. So this is a differential equation, a second-order differential equation with a forcing input of u, and it's modeled by this Simulink block diagram. And so the correlation between these two is as follows. So in this case, u is modeled as a step input, and so there's a block within Simulink for a step input, and that signal u is multiplied by a constant b, where this is also a standard block within Simulink. So that's u times b. Rearranging this differential equation, we can see that y double dot is equal to minus a1 times y dot minus a2 times y plus b times u. So this signal here is the plus b times u. It turns out that this signal right here is going to be y dot, and this signal here is going to be y. This signal y, when we branch it off, the signal remains y. We put it through this gain A2, which multiplies the input signal. And so this signal is A2 times y. Similarly, when we branch off here, this signal is y dot. Multiply it by a gain, and so this signal is A1 times y dot. This is a common element of a block diagram called a summing junction, which we introduced. The signal b times u is on a positive input, while these other two signals are on a negative input. So what this signal coming out of the summing junction is it's negative a1 times y dot minus a2 times y plus u times b. So in essence, this signal is equal to this, which we can see is equal to y double dot, the second derivative of y with respect to time. This block is an integrator, and if you think back to our properties of the Laplace transform, the Laplace transform of integration in the time domain becomes division by s in the Laplace domain. And so that's exactly what this represents. This represents division by s, and so the integral of y double dot is y dot, and if we integrate it again, we get y. This may take a little practice, but hopefully you get a sense of how to translate a differential equation into a Simulink block diagram. One of the nice things about differential equations is that you can include the initial conditions in the model. The way that you do that with Simulink is if you double-click on these integrator blocks, you can set the initial condition. So for example, the initial value of y is set in this block, and the initial value of y dot is set in this block. Furthermore, with these differential equation models, you can include nonlinearities. So there's many blocks within the Simulink library where you could, for example, square y dot, or you could, for example, take the sine or cosine of y and add it simply into your model. An alternative to a differential equation model, if you recall, is a transfer function model. And the way that we find a transfer function from the differential equation is we follow a few steps. First, we identify what the inputs and the outputs are. In this case, u is our input and y is our output. Then we take the Laplace transform of the differential equation and we assume zero initial conditions. So we take the Laplace transform of this, and then we rearrange it into the form of output over input, y of s divided by u of s. And if we do that, this is the resulting transfer function that we get. And so there's a block within Simulink that represents transfer functions. And there are many nice things about transfer functions, one of them being that they're algebraic. So no derivatives, no integrals. It's only multiplication and division by s. They're nice for combining complicated systems, systems in series, for example. Unless, of course, you have loading in your system, then you need to be careful, as we talked about when we were modeling circuits. We also need to be aware of the fact that this transfer function doesn't capture the initial conditions of the system. When we found the transfer function, we assumed that the initial conditions were zero. Furthermore, we cannot represent nonlinearities. So the Laplace transform of a nonlinear function of y can't be performed. So this gives you some ideas of sort of when you may want to choose a differential equation model and when you may want to choose a Laplace transform or transfer function model. So now I will go ahead and open up Simulink and step through a very simple example of how to model a differential equation. So hypothetically, let's say that we have a first order differential equation of the form x dot plus 5x equal to u. If we were to solve this differential equation, we would have a homogeneous portion and a particular portion. Looking at the left-hand side, the characteristic equation of this differential equation would be lambda plus 5. Therefore, it has a root of the characteristic equation of -5. The -5, since it's real, it indicates the rate of decay. So we would expect that the solution x of t would decay like e to the minus 5t. Since there's no imaginary portion to the root, we would expect there to be no oscillation, where the imaginary part tells you the frequency of oscillation. So this is the homogeneous solution. We would also expect a particular solution, which would have a similar form to the forcing function u. If we assume that we have a constant input or a step input, then our particular solution would also have the form of a constant or a step. So if we were to simulate this differential equation, we would expect the response to look something like this. If we rearrange this, we could see that x dot is equal to -5x plus u. So we would imagine that we may have some block for u in our Simulink diagram. It'll go into a summing junction where u is going to be on the positive signal, and then we're going to subtract 5x. So we'll have a negative input. And we'll have some gain of 5 multiplying x. On this signal, we have a positive u. On this signal, we subtract 5 times x. The combination of those two is x dot. To get from x dot back to x, we need to integrate. So we'll have an integrator block, 1 over s, where the output of that is x. We branch that off to get that feedback signal there. And then we'll have this is our output, x. So I'm going to open up Simulink and we're going to recreate this and verify that the response has a form that we expect. We can open up Simulink in one of two ways. One way is to simply type Simulink, the word Simulink at the command line, and hit enter. The other way is to open it from the toolbar. So I'll click on this icon and it will open up the Simulink library browser. If I click on this button, I can open a new model. I can also accomplish the same thing by clicking on the File menu. By doing that, it opens this new window, which has a blank page in it, which I will then create my block diagram, in essence, by dragging blocks from the Simulink library into this window. If you recall, the first block that we need is our input signal, which will be a step. And this input signal you can also think of as a source. And so we will look under this sources library. There are several different sources, types of sources. You can input sine waves, you can input ramps. We're going to use a step. So I click on it and drag it into the window. If I double click on the block, I can change the various parameters. So this step initially has a value of 0 and it steps up to a value of 1. So it's a unit step. I can change that to 5 or whatever. Also, I can change the time at which the step occurs. So as it's set, the step does not occur until time equals 1 second. So I will go ahead and keep these default values. This step input then feeds a summing junction. We can find a summing junction under the math operations sublibrary. If I slide down, I can find it. I'll click on it, drag it into my window. In general, it may take you a little bit of time to learn where some of these more common blocks can be found, but try not to get frustrated. You'll get used to it. If there's in particular a block that you're looking for that you can't find, you can always use this search window to try and search for a block with a name that matches the sort of term that you're trying to locate. So looking at the summing junction, if you recall, the input u is on the positive signal of the summing junction. So I can just click on this arrowhead of the step block and drag it to the summing junction, and it'll automatically connect. The signal that's being fed back, however, I want to subtract. So if I double click on the summing junction, I can change that second sign from a plus to a minus by deleting the positive sign and changing it to a negative sign. That gives me the form that I was looking for. The next block we're looking for is the integrator block, which can be found in the continuous library. Right here, click on it and drag it into our window. If you look, you can see there's also derivative blocks and even a transfer function block. Again, the way we connect, we click on the arrow of the summing junction and drag it to the integrator block. If you recall, this signal is x dot. So if I double click above that arrow, I can add a label to help me remember what that signal represents. I can also double click on the step label and change that to U, so I recall that that's the input. The output of this integrator block is then going to be X. If I integrate X dot, I get X. So again, I can double click above that arrow and put a label for X. This I'm then going to branch off through a gain. And so the gain block that I'm looking for can be found in the math operations library. So I can find it here, click on it, drag it over. The input to this block I want to be X, and the output of this block I want to feed to the summing junction. So I want to flip this block so that it's pointing the opposite direction. I can achieve that by right-clicking on the block, and then this menu pops up, and I can go to rotate and flip, and then click on flip the block. Again, I can click on the gain arrow and drag it to the summing junction. This X is going to be the input to the gain, and the way that I can branch off is to right-click on the arrow, and it'll create a new signal, which I can then drag and connect to the gain block. If you recall, the gain that we want to use is a gain of 5, so I double-click on the block and change that value from a 1 to a 5. And in essence, this models the differential equation. In practice, I want to be able to look at this X variable. I want to look at the output or the solution of the differential equation. And so I'm going to go ahead and store this value in a variable in the MATLAB workspace so that I can plot it. So I can do that by coming over here to the Sinks library. I can get a block 2 workspace, which will send it to the workspace. I could also add a scope or a graph. So this scope, if I branch off, will generate a graph in real time within Simulink. Whereas this 2 workspace block will generate a variable in the MATLAB workspace, which I can then plot. Double clicking on the 2 workspace block, the format in which it's saved, there are a few options. I'm going to go ahead and leave it as time series now. If you're using an older version of Simulink, you might not have the time series option. So in that case, you'll want to use an array. But I'm going to go ahead and leave time series here for now. Click OK. The way that you run the simulation is by clicking on the play button, which is this little triangle. You can also run it from underneath the simulation menu. And as it's set up, this simulation is going to run for 10 seconds. And so that's what this little window right here says. So I click on this. It happens almost instantaneously because it's a very simple model, so it runs very quickly. Clicking back into the MATLAB window, I can see that it gave me this little warning. It says that it's using a default of 0.2 for maximum step size. So the way that the Simulink is set up right now is it's choosing its own step size. In essence, it's using a variable step size such that it uses as large of a step size as it can kind of get away with while still being accurate. And in this case, there's a setting that limits the maximum step size to be 0.2 seconds. That is something we could change if we'd like. When I ran the simulation, it created a couple variables in the workspace. So one is it automatically created this variabletout, which is a time vector or vector of the times that go with the outputs being generated by the simulation. And then there was also this simout variable, which I created with the 2 workspace block. If I type simout at the command line here, you can see that it's a structure where the data info includes all the x values, and the time info has the times that correspond with each x value. So what I can do is I can just plot this SimOut variable, and the plot function understands what the time is and what the x is, and it plots the time on the horizontal axis and the data on the vertical axis. And this is the response that we get. Looking at this, this is sort of what we expected. The step doesn't occur until time equals 1 second. We have a constant added to something that's decaying exponentially, which added together gives us a shape like this. Going back to Simulink, I'm going to go ahead here and I'm going to change this 2 workspace block. I'm going to call it Y, and I'm going to change it from a time series to an array in case you're using an older version of MATLAB, or in case you just want an array of these output variables. So I'll call it X. And I'm also going to create my own time vector. And so going to the library, I'm going to get another 2 workspace block, and I'm going to get a source, and there's a clock block, so I can use to generate time and then store that. So I'll call this time, and I will also save it as an array. In previous versions of Simulink, the default is that it'll save it as a structure. So always go to the 2 workspace block and change it to an array. Recall that in the integrator block, we can change the initial condition. So as it stands, the initial value of x is 0. So I'm going to go ahead and say that the initial value of x is, let's say, 0.1. Recall also that I said that we can change the solver that's being used by the simulation, by Simulink. And the way that we do that is under Simulation, we go to the Configuration Parameters menu. And here we can see that by default it's using a variable step solver, and this is the solver that it's using. So variable step, as I mentioned, is it's changing the time step to make it as large as possible while still keeping the error sufficiently small in the approximation, in the numerical approximation. We can change it to a fixed step solver, and I can choose whatever time step I want. So I could choose a time step of 0.1 second, 0.1 seconds, and then I can even choose the solver. And so here you can see that there's a solver based on Euler's method, which we introduced in the PowerPoint lecture, and it's a first order solver, but you can also use second order, third order, so forth. So clicking OK, return to run the simulation. Again, I hit this little arrow, it runs. Now variables have been sent to the MATLAB workspace for X and for time. If I double clicked on the scope, I get a graph of X versus time without using MATLAB at all. And I can zoom in by clicking on this button, or I can auto scale. You can see that it has the shape that it had before, except here you can see there's the initial condition on X was 0.1. So without any forcing function, the solution is going to just be exponential decay, e to the minus 5t. And so that's what happens. Initially it just decays. This is the free response, or this would be the homogeneous solution if there was no forcing input. And then when the step occurs, we get the same sort of shape that we saw previously. If I go back to the MATLAB workspace, I can now see over here that I now have a time variable and I have an X variable which I created, and I can plot them X versus Y as I've done in the past. Oops. So time wasn't called t, time was called time. This is the figure that's generated, which has the form that we saw in the scope. So initially x has a value of 0.1, it decays, and then at time t equals 1, it responds. Now going back to our PowerPoint presentation, you can see that this is the sort of response that we saw, which is what we expected, an exponential decay with a constant input. So this concludes Module 7. In this module, we addressed a couple of modeling challenges. One, we addressed the situation where it's very difficult to generate a model, a mathematical model for a system based on first principles, either because we don't understand the underlying physics or because the system is just too complicated. Think back to earlier lectures where we discussed what some of the advantages and disadvantages of black box modeling is compared to first principles modeling. So, for example, we looked at using an equivalent circuit model for batteries. And so the advantage of doing that, of generating this black box model as an equivalent circuit, is that we didn't have to understand the underlying chemistry of the battery. So that's an advantage of black box modeling. A disadvantage is that that model may not be widely applicable. For example, the model could be very accurate for the exact conditions and the exact input that was used, but if we tried to apply it in a different situation, it may not match very well. Furthermore, a black box model doesn't give a lot of intuition. So in our circuit equivalent model, we had resistances and capacitances, and we could have found some values for the resistances and the capacitances, but we don't really know what those physically represent. So there aren't physically resistors and capacitors in the battery. So we don't necessarily know what those numbers are related to. You know, what aspects of the chemical reaction, what aspects of the structure of the battery. We also introduced the notion of numerical simulation as a means for getting approximate solutions of mathematical models that are too difficult to solve by hand or are impossible to find a closed form solution for. So that was the purpose. Something to always keep in mind is that this simulation is an approximation of the true solution. So in many cases, the approximation is a good one, but sometimes it's not. We looked at a couple of different approaches to simulation, i.e. ways to structure our system level simulation using either a forward-looking sort of architecture or a backward-looking architecture. A backward-looking architecture tends to run very quickly. A forward-looking simulation tends to be useful for doing hardware in the loop simulation and for doing controller development. We also looked at using Simulink for modeling differential equations and transfer functions, where we saw a few different advantages and disadvantages. So one, with a differential equation, you can include initial conditions. You can also include nonlinearities. With a transfer function, the model is algebraic and it's easy to combine different subsystems.